Hello everyone, this is Michigan State University Human Power Vehicle Competition Team's presentation on the work done up until COVID-19. We have three teams. Artia Azizi will be presenting for roll cage, Alora Van Nest for frame, and Matthew Arends for aerodynamics. Let's get started. In order to construct an efficient rollover protection system, our team's goal was to minimize the weight and its width to allow for the operator to accelerate easier and reduce the drag force acting on the fairings. By referencing previous competition vehicle designs and by conducting an FEA, it was decided that the chromoly steel would provide sufficient strength for the operator's protection. The dimensions of the steel were selected to be 1/1/8 OD with a 65 thousandths of an inch thickness. The top of the roll cage was bent to form a half circle with a 6-inch radius to reduce stress concentration buildup, and a 32-inch width was decided to be slim enough to reduce the drag force acting on the fairings while providing enough clearance for the operator's shoulders. The RPS also has 3 points of attachment. A hollowed out cylindrical aluminum block serves as the main point of attachment near the middle of the frame, and 2 support bars secure it towards the back of the bike. 2 RPS testing were planned to be completed, the fall and the rollover one. As seen in the example photo in the middle, that would be in the case of a fall, where the vehicle moves from the upright position to resting on its side, with the RPS preventing the person riding from contacting the ground. The width of the roll cage being 32 inches ensures the person on the bike will stay intact while wearing the safety harness. The rollover testing shows the vehicle from an upright position to an inverted one while the person's body does not make contact with the ground. These testing were to be completed during the month of March. An FEA was done using CAD models of the RPS and the brackets that support it. The top load of 2670 newtons at a 12-degree angle generated a max deflection of 2.838 millimeters, and the side load of 1330 newtons generated a deflection of 2.838 millimeters, both well within the set limits.
Our goal for the frame this year was to optimize adaptability, efficiency, and effectiveness. We chose to reuse the base of the frame from the 2019 competition and modify it to better accommodate different riders. One of the main ways we did this was with an adjustable seat system. We reused the base of the seat because it was extremely ergonomic and lightweight, but redid all the attachments. The seat attached to the frame in 3 spots, once under the seat with 2 back extension rods. We added 2 new attachment settings to the bottom of the seat by welding aluminum tubing, and remanufactured the extension rods so that as the seat moved forward and back, the rider could remain in the comfortable position. As a worst-case scenario, all attachments were tested at a full-body loading, the bottom in shear, and the back extension rods in bending. The FEA showed no signs of failure in either case, indicating that our system was ready to ride. We removed the old handlebars from the frame and manufactured 2 new sets, one that was optimized for rider control for the endurance race, and one that was narrow and fit within our fairings for the drag race. Both sets of handlebars were made with adjustable height settings to further personalize the riding experience to the rider. FEA was in the works for both sets when we got the word about the EFES cancellation. It was to be followed by field testing for rider comfortability shortly after. The original frame only had front brakes, so we decided to add a rear wheel braking system to increase braking force and give the rider more control. We decided to install a disc brake using an attachment we manufactured due to its fatigue resistance and minimal manufacturing time. FEA ran at the maximum possible braking force, produced a minimum 2.1 factor of safety, meaning that at the worst case scenario, our brakes would remain intact.
This semester's aerodynamics team focused on a variety of ways to reduce the drag of the vehicle. The main addition that we added were extended side fairings down the sides of the vehicle. Based on hand calculations, we estimated an 11% reduction in the drag coefficient CD, which meant in order to offset it, we could add less than 40 kilograms, which gave us a lot of room to work with. The idea behind extending these side fairings is to keep the flow attached to the vehicle for a longer length. Attached flow decreases the pressure differential between the front and back of the vehicle, therefore reducing profile drag. In order to attach these extended fairings to the vehicle, clips were fashioned like those shown in the smaller picture. These clips were attached to the fairings and then clipped onto the roll cage. There was also buckles used to attach the side fairings to the front fairing. In order to validate these design additions, some CFD testing was performed in ANSYS Fluent. This test proved that the new fairings resulted in a decrease drag coefficient of 38.9% of the previous value. Some of the pressure contours from this testing are shown on the left, and you can see in the top image that there is a much bigger pressure differential between the front and back of the fairings compared to the bottom image. To further validate these design additions, some real-world testing would be performed. These tests would involve a wind speed anemometer to measure the velocity of the vehicle relative to a cadence of pedaling. This test could be performed both with and without the side fairings, and we could isolate drag in the measurements in order to further validate the additions that were made. That wraps up the MSU Leonidas presentation. Thank you.